Okay, so I guess first came this. We have a core. We call them kind of interchangeably cores and PMD cores in OVS. We have a core. It pulls some queues from some DPDK ports, so port 0, port 1. It processes the traffic. It's run to completion, and it transmits it. But of course, what's the problem? That maybe these queues are very busy, and as Jan showed us in some of the earlier presentations, while packets from port 0 are being processed, maybe packets from port 1 are building up on the NIC, and they end up getting dropped. Okay, so then we said, well, how about we have 2 cores, and we can assign a core per port, and that way we can avoid one core preventing another core to be processed. So in this case, that's fine, but again, even on the DPDK port 0, we could have a lot of traffic, and maybe there's some decapsulation, and maybe it needs to go to VM, so we could still end up with packet drops. Okay, so then came multiple receive queues. So now instead of having one queue per port, we can have multiple queues per port, and we can assign a core to each one of them. And that way we can split our traffic through RSS on the NIC, and again, we can scale out the performance. And over the years, we've seen performance graphs at this conference that have shown that it scales very well. But what happens, but how do we scale that? We don't have an infinite number of cores to match each port. So say we take away one of these cores, we maybe take away on port 1 core 3. What do we do with that other RX queue? Okay, we have to put it somewhere on one of the other queues. And how do we do that? So we have to have some algorithm. So typically what we've done is we've just cycled through the list of ports and queues, and we've just placed them on whatever the next core available is. Okay, so what if something like this happens? We have a really busy queue on DPDK port 1, and on DPDK port 0, maybe the traffic is lightly loaded. Or maybe the DPDK port 1, the traffic is very important that we want to ensure it gets cycled. And again, on core 1, we get back to the situation where we have some packet drops. But maybe core 0 has lots of free cycles, and that seems like a really not bad situation where we have lots of free cycles available on core 0, but we're out of cycles on core 1 and we're dropping packets. Okay, so then manual pinning of queues came in. So we could say, okay, well, let's pin this port 1 Q0 to a core, give it a core all to itself, nothing else can be placed there. And that's quite useful, I think, but it doesn't scale, so for a few reasons. Number one, we might know what cores are going to be busy, if it's just general traffic, if it's and we can't scale in terms of pinning multiple queues maybe beforehand. Okay, so for that DPDK port 0, we're only showing one core here, but there could be maybe multiple queues and several cores there. And again, we get back to the situation where OVS has to round robin and assign the queues to each core. Okay, so there's another way to do it. So if we looked at that similar situation and we said that the port 0 was fairly lightly loaded and DPDK port 1 was very heavily loaded. So we have on core 1, we're using maybe 30% from RxQ1 and 70% from the other queue, and we're dropping packets. The core is very busy loaded, so 30% of the cycles available on the core, and the other one is pretty free. So how about we use that information, and the next time we have to assign the queues to the cores, we try and do it a little bit smarter. So we try and use that information, and we try and place the queues in a way that gets the best or a better usage of the free cycles. Now, one thing to say is that this has been done very conservatively so far. So they're still around robin, so the queues will still scatter amongst the cores equally. But what we've done is we've picked the queues with the highest amount of cycles recorded, and we've tried to place them on different cores. And there's a few reasons for this. So the thing about historical data is that it's historical data. Okay, so it's no guarantee of what will happen in the future. And the other thing is we could also have maybe queues that are new or just being brought up that have maybe no history. So the more we try and optimize based on historical data, maybe if we have 20 queues that use 5% each, sure, we could put them on one core, but it makes it more, more susceptible to breaking and having packet loss at the moment. But we could look at trying to make it a bit more aggressive in the future. Okay, let's demo. Okay, so what I have here on the left-hand side, is it readable? Okay, what I have here on the left-hand side, I have a device under test, 2 windows to that. And on the right-hand side, I have a packet generator. So on the left-hand side, there's OVS-DPDK running in the top window. We've got 2 cores, core 4 and core 6, and 2 ports, DPDK port 0 and port 1. And as you can see, DPDK port 0 has got 2 queues, Q0, 1. And what we'll notice is that DPDK port 1 has 1 queue, and it's placed on core 4 with one of the queues from port 0. So in this test, what we're going to do is make the kind of busy queue, the fat queue, for DPDK port 0, and we're going to make DPDK port, for DPDK port 1, and we're going to make DPDK port 0 fairly lightly loaded. I guess I was supposed to talk while this was playing. Okay, so if we pause it there. So the auto balancing, or the balancing stuff is all there already. So what I added in is some stats that I haven't submitted yet. And we can see on the left-hand side, on core 4, that DPDK port 0 is using 29%. Maybe I need to let that converge a bit more. Okay, so we're hitting up on 100% on core 4, whereas on core 6 we can see we're using about 45%. So we know we're kind of maxing out core 4, and we know there's free cycles on core 6. And if we look at the packet loss over here, so where my mouse is there, we can see, if you can read it, that we're sending about 18.6 million packets per second. So just over here. And what we're receiving back is about 15.6. So we're losing about 3 million packets per second. Okay. So now we would do a rebalance through any natural change, like a reduction in queues or an addition of cores. But we put in a command that would also do the same thing. Okay, so if we go back over to the left-hand side and we look at how it's been distributed now, we can see that DPDK port 1, it's recognized that queue was, its only queue was using a lot of cycles, so it placed it on its core of its own, and then the other 2 lightly loaded queues, it put them on the 1 core. Now again, that's not really packing, that's just round robin with the amount of queues I have in this test. And if we go over and we look at the statistics now, we can see we're sending just about 18.6 million packets per second, and we're receiving about 18.6 million packets per second. So we're making better use of the cores that we have. So that's there at the moment. I say the statistics, I have to do a little bit of work on them just to clean that code up and submit that. There's definitely some improvements we can make to it. So one thing is that like 1 cycle could potentially change where queues go. So we want to try and reduce that and maybe make it a little bit more coarse-grained. For some queues, there's no need to move them maybe. So there's some possible improvements in the future. Okay, that's it.